Okay.
No, I know. Do I talk loud enough? Can you guys hear me?
Yes.
Okay. Change my glasses here. Okay, just a quick one. You probably heard my accent. I was born and raised in the Netherlands, Holland, that is, in a small town very close to the North Sea, the ocean. A great place to live. And in 1970, the wife and I, we decided we're going to immigrate to Canada because I had two sisters in Canada, so we did that. So we came to Kitchener in 1970 and lived in Kitchener for 13 years, and then we moved, believe it or not, to Wawa, because I started a job with the Canadian Broadcasting Corporation to maintain TV and FM transmitters. To make a long story short, from there I went back to Kitchener in the two-way radio field, which I had been in before, and I went back to the CBC, and then after that I went to the OTP, maintaining their communication system in the 14th district, as it was called, which was all the way from Hornpain, White River, Shotlow, to Elliott Lake and the Sioux area. So that's what I needed. And my last name is pronounced Lee Veld. The E in Dutch is pronounced as an A. So that's why some people have difficulty pronouncing this. I've been called everything under the sun, but never late for dinner. So. Anyway, my call sign is Victor Echo 3 Delta Whiskey India, or some people call me Victor Echo 3 driving while impaired, or driving while incontinent, or whatever you want. So anyway. Okay, now I've done a lot of the kind of semi-difficult stuff with the resistors in series and parallel. But what follows out of that is we're going to do some calculations with the Ohms Law. So we have two resistors in series, and we apply a voltage to that. This is the symbol of not a battery. Officially, this is only one cell, but generally we say this is a battery, okay? So in that case, what I'll do is I'll get rid of the battery, and I'll just say we have a DC voltage source here of 10 volts DC. And we have a resistance here of 5 ohm, and we have a resistance here of 5 ohm. Now, according to Ohm's law, we want to calculate the current through this circuit. And Ohm's law says that the current equals the voltage divided by the resistance. So the current here is, the voltage is 10 volts divided by the resistance. Now we'll make this easy. We know two resistors in series, we add them together, becomes 5 plus 5 is 10 ohm, right? So we take 10 divided by 10 equals 1. So the current flowing through this circuit is 1 amp. I'll write it as amp, but normally we only put the capital A down. One thing we gotta keep in mind, when we do calculations, all the parameters have to be in their standard value. If the voltage is in volts and the resistance is in ohms, the current will be in amps. So we also talk about milliamps or microamps. 1 amp, a milliamp is 1/1000th of an amp. So 1 amp contains 1000 milliamps, right? Okay. So you can also calculate this and say, I want to know how many milliamps it is. Well, you know it is 1 amp. A milliamp is 1/1000th of an amp. So you can say the same thing by marking this down as 1000 milliamp. That's the same thing as 1 amp. Okay? So let's not go too deep into that right now. So, 1 volt. Since we have a current flowing here, we also know that the resistance that we find out, the voltage that we can find out, E equals I times R, right, according to Ohm's law in that triangle that you have. So we know the current flowing through this resistor is 1 amp, but that same current flows also through this resistor. And it flows down this way, and it comes back to your source, your voltage source. So this circuit has a current flowing of 1 amp. So the voltage across this resistor, here to there, is equals E voltage I times R. We know the current is 1 amp. We know the resistance is 5 ohm. So 1 times 5 is 5. So the voltage across this resistor is 5 volts. That makes sense? Everybody understands that? Get that, Joe?
I'm sorry, I wasn't paying attention.
Okay. If there's a current of 1 amp going through both resistors, and the resistance of this resistor is 5 ohms, according to Ohm's law, the voltage across this resistor is E equals I times R. Remember the triangle? Here you have E, and you have I, and you have R. So E equals I times R. So I is 1, the resistance is 5, so 1 times 5 is 5, so the voltage across this resistor is 5 volts. But we have 10 volts. So that's interesting. That resistor only drops what is called 5 volts. But there was another resistor, and it too is 5 ohm. And the same current of 1 amp flows through it as well. So the same thing applies here. I times R equals E, so we get again 1 times 5 is 5 volts. So each resistor drops 5 volts. Add them together, 5 and 5, and we come back to 10. So we know now that the 10 volt power source with a current of 1 amp, the resistors 5 ohms each will drop 5 ohm. Alrighty? Now let's make this, let's make this 3. So now we're going to have to calculate the current because we changed the resistance. The voltage remains the same, so the current has to change too. So now you add again the resistors, 5 plus 3 makes an R total of 8 ohm. So the total current, I equals E divided by R. E is 10, R is 8, so I is 10 divided by 8. Somebody on the calculator?
1.2.
1.2?
1.25.
What is it?
1.25.
1.25. So now the current is not 1 amp, but 1.25 amps. How much voltage will be dropped across this 5 ohm resistor is now again is E is I times R is 1.25 times 5 is what, 6.5 or 25? What's 1.25 times 5?
6.25.
6.25, right. So we have 6.25 here now instead of 4 or 5, I mean. That's the voltage across it, okay? Should have drawn it here. So now we have the current again of 1.25 through a 3 ohm resistor. So the voltage across here is 3 times 1.25 is 3.75. We add 6.25 and 3.75 together. What do we get again? 10 volts. Excuse me. So we know our calculations are correct. So if we have a whole bunch of resistors in series, each resistor will drop a certain amount of voltage depending on its resistance and the total amount of current that goes through it. The current, the total current is going through every resistor because they're all in series. It cannot be 1 amp in one resistor and all of a sudden now it's only half an amp in the next resistor. That's impossible. So the current through that circuit, resistors in series is all the same, and you can calculate the voltage drop across each resistor by taking the current times its resistance. And when you've done that and you add them all together, you should come up to the same voltage as your power source. So there again, you have a double check. You can double check yourself. What happens now with resistors in parallel? We'll start again easily with 2 resistors in parallel. Draw the dots so we know they are connected. And we bring this back here again, and we'll use the same 10 volts. And we'll make this 10 ohm and this one 10 ohm to make it easy. Now what's going to happen here? The current will split into 2 paths. Part of the current will go through here, and part of the current will go through there. Okay? But first, we want to know what the total resistance is here. Can somebody tell me quickly what the total resistance of this is?
5 volts.
5 volts, exactly. Again, you have 2 resistors of the same value. The easy way is you take the value of 1 divided by the amount of how many resistors we have, in this case 2, so the total resistance becomes 5 ohm. So now we can calculate the current. I equals E divided by R. So we take 10 divided by 5, so I becomes 2 amps. Correct? When I say correct, you know, everybody says, am I right? Is he right? No, it is correct. 10 divided by 5 is 2. So there's 2 amps going through here. But since these resistors each have 10 volts across them, how much current will go through each of them? 1 amp. Right on. 10 ohm, 10 volts, 10 divided by 10 is 1. So we have 1 amp going through here, and we have 1 amp going through here, which in total added up is 2 amps. I would say, you know, 1 amp here, 1 amp there. That's not true, of course, because the current flows in that direction. So, but anyway, yeah, they both go this way and they come together here. Another one of, it's not Ohm's Law, it's actually Kirchhoff's Law, but that is not on your exam, but I will mention it. That says that at a junction where the current splits out into different currents, when they come together at the nth junction, they all should add up to the same. So what goes in has to come out. You don't change the current on the output. The total current on the output is the same as the total current on the input. And we can see that here. 1 amp goes this path, the other amp goes this path. When they come together, it will become 2 amps again. All right? Make sense? Now, if we had another resistor here in series, for example, and it is 5 ohm. Now we calculated this to be 5 ohm, and now this is 5, so we have again 10 ohm in series altogether, so we would have 1 amp again. So what happens then? There's less current going through here because there's less voltage across those 10 ohm resistors. So. Okay, any questions on this? So in simple form, which never is simple of course, especially when you're starting out with it, but in a simple form, you bring everything back to a basic configuration. Resistors in parallel, you bring it back to 1 resistor. Resistors in series, you bring it back to 1 resistor. If you have parallel and series in combination, you put them all first back to a normal 1 resistor, and then you add it up or whatever. And that makes it a lot easier to do the calculations. I should follow
It
this.
doesn't matter which order you do them in.
No,
You can add this series ones together and then use that, add with the parallel one, make a parallel into one, or the other way
yeah,
around. or
which
whatever.
it depends on the configuration of them. If you have 3 resistors in parallel, it makes sense to do those 3 first and make them into 1 resistor, etc., etc., etc. So you'll see enough examples in your book, in your study guide. Go through them, do the calculations, or at least follow them, and see if it makes sense to you. All right, power. We know if we turn the light on, and we have the old incandescent lights, and the light starts to burn, it has 120 volts applied to it. Depending on the size of the lamp, it will draw a certain amount of current. But we also see that light lights up, and it provides not only light, but it also provides heat. A lamp, a light bulb, is nothing more than a resistor, okay, which glows. So it gives off light and it gives off heat. There again, people say, ah, well, I got so much light, but I lose a lot because of the heat. No, you don't lose the heat, especially in the winter. You know, you got 20 light bulbs in your living room, there's heat coming off of it. Now your furnace has to burn less because the heat that's dissipated by the light bulbs still is in your living room and heats your living room. So again, that power, as far as the light bulb is concerned, it is a kind of a waste of energy. But that waste of energy helps us by heating our room. So again, energy cannot be lost. It goes transformed into a different kind of energy from light energy and resistance. It transforms itself into heat energy, but it is not lost. So we have 120 volts AC, because that's what is in our outlets. So I just write it as AC, but it could be the same for DC. I'm not going to go into detail about that. And there's a light bulb here. Here. Now, if this is a 60-watt light bulb, we want to know what is the current going through that. Well, with Ohm's law, we had voltage and amps, and we had resistance. But there is another part of the formula that tells you how much power you are using or dissipating in that resistor. And the power is voltage times current. And the power stand, the P stands for power, but it is measured in watts. And I guess that came from James Watt, who invented the steam engine, and somehow they have made the expression power in watts named after him. So, if this is a 60-watt light bulb, so we have in this case 60 equals, and E is 120, and now we need to know the current. So what are we going to do now? P is E times I, so I equals P divided by E. So I equals P divided by E is 60 divided by 120. And how much is that? Half an amp. Okay? So the current flowing in this circuit is 0.5 amps. Now you can double check yourself if you have made your calculation correct, because the basic formula, power is voltage times current. So now you say, okay, voltage 120 times current is a half, becomes 60. So your calculation was correct. You can double check. So this light dissipates a power of 60 watts. Maybe 50 watts in light and maybe 10 watts in heat. I don't know. But in total it dissipates a power of 60 watts. Does anybody know how much power in wattage a horsepower is?
740, was it? 746.
746.
Or 740.
700. Again, depends. If you're in Great Britain or in Europe, sometimes they call it 736 watts. Here they call it 746 watts. So, but in North America, 1 horsepower is 746 watts. Power is always expressed in P in watts in our electrical theory. So the same as this sheet that I provided you with, if you look at the center circle, we have P for power, I for current, R for resistance, and E for voltage. If we go clockwise in the center circle. Now if you, for example, take the P for power, if you go to the left it says EI. They didn't put the multiply sign in there, they just put EI, which means E times I. Right? It's the same as here. Power equals E times I. So power is E times I. Now if you have the current and you have the resistance, you can take this formula. It says I squared times R. That gives you the power as well. And the one above that, it says E squared divided by R is also power. So as long as you have any of the two, you can always calculate the third one. On the right-hand side, top right, it says I for current, and above that it says I equals E divided by R, or I equals P divided by E, and remember that's what we did here to second guess our calculation. Or I equals the square root of P divided by R. Now you can remember, you can memorize those formulas, and it is nice if you can do that. But don't forget, you can always derive, as long as you have two, you can always get to the third or the fourth. And the same with ohms and volts. So this multiple circle thing is really quite handy. If you see on the bottom, it also has the formulas. R, here they call it equivalent. It didn't come out well in the copying, but it's R means REQ, R equivalent, equals R1 times R divided by R1 plus R. That's the simple one for two resistors. And beside that, to the right, is the one if you have a number of resistances in parallel combination. And then again, they say 1 divided by R equals 1 divided by R1 plus 1 divided by R2, etc., etc. We have done those calculations using this formula. The one on the right-hand side, forget about it for now. On the back of it, I put down engineering units. If you look at the middle section, it says the base unit, like 1 amp. Remember I said you can change that into milliamps. 1 amp is 1,000 milliamps, which is 10 to the power of 3. It becomes a kilo. A milliamp is also 10 to the power of minus 3 of the base unit. A micro is 10 to the power of minus 6, which is 1/1,000,000th of an amp. A nano is 10 to the power of minus 9, which is a nanoamp, and then there's a picoamp, a picofarad. You'll have to look at that in conjunction with what you have in the study guide. All right, again, you have these formulas in your book here, and it covers everything what we have gone through tonight. Some of it may be in more detail, but I've tried to explain to you how it goes and how it works. Any questions? That's good. Well, yes and no. But it means that everybody is in agreement what I've talked. Nobody caught me with a lie so far, which is a good thing. Okay, I'm going to do a few practical things here. First, I'm going to show everybody the type of resistors that we have. This resistor is a wire wound resistor. When you see it, you can see that it is actually a wire that is wound on a ceramic body. So that means it is a power resistor. It can dissipate quite a bit of power. And in this case, it says the value on here is 500K. What do you think 500K means? 500 kiloohms or 500,000 ohms. A kilo ohm is 1,000 ohms. And then it says behind there 1%, which means the accuracy of the resistor, the tolerance is 1%. So 500,000 ohms, what is 1% of 500,000? That is 5,000, right? So it could be 5,000 ohms higher or 5,000 ohms lower. Let's measure this. I have the setting here at ohms, and I'm going to put my trusty meter on here. And it says, yeah, I got a poor connection here. Okay, 390 roughly. So it is 390 ohms, 1,000 ohms that it says here.
In that first class, we found a little difference if you hold your thumbs on it.
Oh yeah.
So you've got to keep your hand.
Well, you got to be careful, especially with a high resistance like this, 0.5 mega ohm, and that's probably one of the reasons. Everybody has a resistance. Your body is a resistor as well, and depending on the amount of moisture in your body or on your body, your resistance will vary. Because it is fairly warm tonight, and I may have some moisture on my hands. If I now grab the probes, yeah, it says 1.5 mega ohms. Now if I'm going to start squeezing and get a tighter connection, it drops quite a bit, right?
Exercise and water too.
Yeah, it says 610,000 ohms. So depending on how high if I go wash my hands and I come back up and I touch it again, you will see the resistance is far less, far less. That's another thing that with electricity, you don't fool around with electricity, especially when you are wet. I worked in Holland as an electrician. I was called out to a greenhouse complex where they were heating the greenhouse with steam, and steam in the pipes. But when the steam, of course, cools off, it creates condensation, which gets brought back to where the boiler is, and there's a pump that takes this condensate water and it pumps it back into the boiler. The pump had its own little enclosure. It was just a shed with a sand bottom. The soil, the floor was made out of soil, not concrete or anything. And I was called out to go there. I went there on my moped. It was raining. I was wet, and I go there, and the light wasn't working in that room, so they couldn't see what they were doing. So I go in there, and I walk in, and I look at the light, and it was a fluorescent light with a metal screen around it for protection. So I grabbed the metal screen in order to open it so I could get at the bulbs, and as I grabbed it, my hands just started cramping up, and it wasn't grounded. And there was 120 volts on that screen. And here I am standing there, my body is wet, my shoes are wet, the ground is wet because it's steam all over the place, so it always very damp. And my fingers just went like that, my muscles were grabbing it contracting because of the electricity flowing through me. And I still say the only reason that I stayed alive is two things. First of all, I was young, so my heart was still strong. Secondly, the moment that happened, I immediately lifted myself off the floor. And I broke the connection between my body and the ground, because the current was flowing through my body to the ground. Not between my arms, through my heart and there, but it went through my body to the ground. So I lifted myself off the ground, broke the connection, I let go, and I dropped to the floor and I was okay. But I learned two lessons. First of all, you don't believe whatever they tell you, because he said he had turned the power up, which he didn't. Secondly, the light switch was on too, but the light wasn't working. So initially I walked in and said, oh, the light isn't working, so something's wrong, the light switch is off, the fuse is blown, and I should have never touched it. I should have first made sure that the power was off. Because my body was wet, the ground was wet, I provided a very good path for the current to flow through me, and there was enough to contract all my muscles together. So be very careful. High voltages and even low voltages are dangerous. Okay, let's say wire-wound resistor. Here's another resistor. That's a typical example of what they call a carbon type resistor. The smaller resistors that we mostly encounter, like these, I think this is a 1 watt, maybe a 2 watt resistor, is carbon, and the carbon is of a certain size, and that determines the resistance. Now here what they've done, because it is capable of dissipating a lot of power, they took a ceramic type body and they laid the carbon layer on top of it. And then the ends you see that looks like gold, and it may very well be a bit of gold, to make the contact. They actually go into metal springs like that. This is a 50 ohm resistor, and that is used for a dummy load. You will later in the class, and you will hear about and understand what a dummy load is. In order for this to be able to dissipate the power that goes through it, they have it actually mounted vertically, and it's in a bath of mineral oil or transformer oil, which then will cool it and dissipate the heat that this dissipates, and therefore it can actually handle 1,000 watts of RF power from a transmitter for probably 30 seconds. So don't drop it, please, because that is the only spare I have for my dummy load. And when I say dummy load, I don't mean my wife. We have called her affected, you know,
she's gonna watch the video
on the radio a few times, you know, where's your dummy load? Oh, she's cooking meals, you know, and she knows that.
When did you eat that night?
Don't say it too often. Okay, here is a resistor which is also a fairly somewhat precision resistor. It's 100 ohm. This one states 100R, which indicates it's 100 ohm, and it's 5%. Let me just, since it's 100 ohm, it's fairly low, I can fairly safely just use my fingers on it. It was off. I just have to set it here. Okay. It says OFL for overload or something like that. Okay, this automatically determines the range, and it says 100.5 ohm. So that's a pretty good resistor actually. And there's many more.
5%, right now?
Yeah. And just for the heck of it, some of these, the one was probably 5 watts or 10 watts, and the one was 2 watts. This one is probably a ½ watt resistor size-wise. And then there's a tiny one here that is 1/8 of a watt. If you drop it, you'll probably lose it. Now you think that is small. It is a very small resistor, but nowadays with the printed circuit boards, etc., They have gone to what's called SMT, surface mount technology. So the resistors are actually laying on top of the circuit and soldered in instead of the wire of the resistor going through the board. I brought this as an example to give you an idea. This is a flexible circuit board. I can bend it, twist it, and nothing goes wrong with it. But if you look at it, you see these tiny little things with numbers on them. That are also resistors and capacitors. Okay? So, the various types of resistors. And on the one sheet, it showed you also the color code, the chart for the color code. So when you have a resistor with the color code on it, you can determine what the value of it is.
Should we have that memorized for the test?
Yeah, you should memorize that. It's not too hard to memorize, as long as you memorize what each band does. Like the first one is the first letter or the first number of the resistor. The second one is the second number, and the third band is the multiplier. And the multipliers go from 1 to 10 to 100 to 1,000, etc. So it's not too hard to remember that actually. Also, you have to know the phonetic alphabet. It's called the NATO phonetic alphabet. The old alphabet in the telephone industry, they used person names, John and Mary, etc. Well, they don't do that anymore. It's all standard now. Both the military and amateur radio operators and many other outfits, they use the NATO code, and that's what this one is. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf, Hotel, India, Juliet, etc. And this is in pictorial format that makes it actually a little easier to remember, okay?
Can I ask you, on the pots, like we were looking at one on Tuesday, I didn't see any resistance values on this. Are they marked on there?
A lot of them don't show the resistance value. This one does. It says 1 kilo ohm.
Oh, okay.
So
the other one just had a part number, so would you have to look it up in their books?
Or you take your trusty digital reader and you measure it, okay? This one here too, if I go across both outside terminals, it should give me the resistance. It says 1,042 ohm. So
The middle is the ground?
Hmm?
The middle is the ground?
Not necessarily, but it is in this case because it's all connected to the threaded bushing here. So where you mount it on the chassis, it is actually grounded. But the 3 terminals are floating, they're not connected to the outside.
Okay.
So you can use this as a variable resistor, which a volume control is. It is a variable resistor, okay?
So all of them don't have the numbers on them, okay?
Not all of
I've
them
seen
have
some of
the
them
numbers
that
on
don't
them.
have it.
This one here, for example,
Oh yeah, this is nice. I like this.
yeah, no, this one doesn't show it. These are 2 potentiometers in one with 2 shafts. It doesn't have the value on them, so you got to measure it. Also, as we were talking about resistances, etc., you know, a piece of wire is also a resistor. No matter how large or how small, a piece of wire is a resistor. Now, probably we all know that in our household electrical system, in our homes, most of the wires in there are what they call a number 14. Number 14 is rated at 15 amps by the industry. So you should never have a circuit breaker or a fuse larger than 15 amps on a circuit that has a number 14 wires in there. Because if you put too much current through it, you increase the size of the fuse, it blows on you the fuse. Oh, I only have a 25 amp, put it in there. The circuit could draw 25 amp, heats up the wire, you could get a 5 amp. That number 12 wire is good for 25 amps. That's what they mostly use in kitchens because you use heavy duty appliances in there. Yeah. So the various sizes of wires, as it is, I always found it confusing. The larger the number, the smaller the wire. It's AWG, American Wire Gauge. Here we have a piece of cable. It's got a number of wires in, and they are number 24, small wire. Okay, this one here is also a small wire. I think that is number, 16 AWG. So this number is smaller than that one there, so but it can carry a higher current, even though it's still a fairly small wire. This one here is a number 8. Now again, different kinds of cable. Both of these are a number 8 wire. This one has a multiple core of solid copper wire. It's stiff. It's not that easy to bend. But if you take this one with the same size wire, it has multiple thin wires, and it's very flexible. I can bend it.
Will that carry the same amount as this one, even though it's
Yeah,
solid?
same amount.
It doesn't matter if it's stranded
No,
or
no,
solid. It's
no.
the same.
If it is number 8, it'll carry the same amount of current.
Oh, so they compensate, because the stranded wires have airspace in between,
Yeah.
so it's gonna be less
They compensate for it.
surface area, okay.
This here is a number 4, number 4 AWG. That is fairly flexible. That one. Yeah, here's another number 4, but it's not as easy to bend.
This one here has foil in it. Is that for grounding?
That's a shield.
For grounding
Yeah.
in case any of them are shorting?
Yeah, no, this is just a shield that shields it for RF
Oh,
interference, etc. That is a cable that is used as a control cable for various things. Now here's what they call a 2-aught wire, 2-0. That's a very heavy wire. It can, I don't know, I didn't look it up, I should have, but I didn't, but that can probably carry 200 amps, I would imagine. And you can see and feel the difference in size. Okay, again, this is another heavy-duty ceramic resistor that can dissipate a lot of heat. It is 30 ohms, that resistor. 30 ohms. So if we apply voltage to that of 300 volts, what would the current be? 300 divided by 30, 10 amps. 10 amps and 300 volts is 3,000 watts. So that would dissipate a lot of power. You would never put that through there, there'd be too much, of course. That's about it in a nutshell. I at times got lazy, and instead of remembering the color code by heart, which I knew very, very well actually at one point, I have a little calculator here that came from Radio Shack, but they do not sell them anymore. And if you find one, hang on to them, because they're not just valuable, they're useful, and they're kind of rare now. I just dial up the color code of the resistor. Orange, let's make this green, and this one here brown, and it says the resistance is 250 ohms. So it's easy to do it that way.
You even have apps there now for it. There's an
Yeah,
app actually
oh,
on
yeah,
the
I
phones
got it
that
on
have,
my
yeah,
cell
they're
phone.
nice to have.
Okay, ladies and gentlemen, I think that's it for tonight. For next week, study your chapter. Make sure that you at least are familiar with it. And next week going to be a little tougher, okay?
Thanks, Tony.
Okay, you're welcome.